a visit. Right? It's not possible to do that. So count data really is a special class of discrete data. Right? It's discrete in the sense that it takes on a definitive set of values. It can't take on any value. But it's integer data. Right? It's integer data. So it's 0, 1, 2, 3, 4, 5. It's not the real number line where we can have any number on the real number line. Right? And when you think about distributions of counts, has anybody ever looked at distributions of count data before? No? Generally what we see when we look at the distribution of count data is that in general, count data tend to take on a really interesting distribution. They tend to be distributed like this. Right? So how would you describe data that look like that?
Like a whale.
They're not necessarily a whale.
Right.
Oh,
But it's right skewed, right?
yeah.
No, we'll get to that because it's important. If it were a whale, then the tail would be coming out to you this way. Right? That's the difference between a mammal and fish.
Wait, what?
I'm learning so much.
Say again?
Why would we
Have you guys ever been to like SeaWorld or something?
Yeah.
Mammals.
I was just SeaWorld yesterday.
Were you really? Marine mammals' tails, their tail fins are flat. They go up and down. Fish go back and forth.
Yeah, but wouldn't that tail still be going?
No, this is if I were to draw a fish, right?
What's going on?
You draw it like that. Right? You draw a fish like that.
Oh, I thought that was the whale's head.
No.
Oh yeah.
Okay, all right. Anyway, so back to this skewed distribution. Back to this skewed distribution here, right? So if we were to describe this skewed distribution in words, how would you describe it? What's going on? Without technical jargon, what's going on? It's right skewed. But what does that mean to be right
Well, the
skewed?
majority of the values are on the left. There's sort of the values on the right stand out.
So what does that mean? The higher the count,
Fewer the values.
the fewer the values, right? So the higher the count, the less likely you expect to see that higher count value in general, right? We see that a lot with count data, right? Is it up and running? Yeah. Okay. Well, let's have some fun here. Let's see if this is going to work for us.
Is money in this category?
Yes, but money's different. Yes. The answer is yes. Huh? Oh, get that. Go back. Please go back.
Supposed to be Thursday.
If you press it too much, it gets angry.
Go back. Okay.
But it started. It started to move.
Pressing the buttons I normally press and it's not working.
There it goes. I do remember staying up doing that real quick. You're right.
So anyway, somebody said it looked like a whale, which is kind of funny. Because the first model that was developed, it's not working. Well, whatever. Come on, screen. Well, we have the Little Mermaid playing. It's just not paying it. It's not cooperating with us. Well, the first model that was developed to look at these data, these kinds of data, there we go. I wish we had sound because the song that's playing is Poisson.
Oh,
I was seeing it all week.
That's right.
All right. Well, I can't get sound. That's the issue. Anyway, so if you were to draw a fish, right? You might draw it this way, right? Something like that. And if you were to look at the shape of this, it kind of looks like a fishtail. So this guy, and we'll talk about the guy who started, anyway. Huh? Is it playing like this? Is it for me? Oh, you got it. All right. Le poisson, right? So here we go. Le poisson. So le poisson means fish in French, right? So, okay. Let's talk about this. All right. So let's talk. We'll get into why. Well, now we understand why it's called a poisson bait, because it's shaped like a fishtail. A little bit of humor here for us. All right. So we talked about the characteristics of count data, right? Can't be non-negative. Lower bound is 0. Right? We're dealing with integer data, right? Whole numbers, right? When you plot your data with counts, the histogram tends to take on this. Now, this is a smooth distribution, right? So this is smooth because these things are all connected, and this is a nice transition from one thing to the next. This sort of gives the point that it's continuous data. When you have categorical data, it's really, discrete values. Make sense? So it's not smooth like I've drawn it here, like that, okay? One also thing to consider is that in most cases, the distribution is not normal. Not normally distributed. It's not symmetrical, right? So the data, there have been distributions that have been developed to help model data that take on these characteristics. The first model that was developed by, I think, the guy was one of Napoleon's generals. He called it a Poisson distribution, which was interesting for his set of data. But what we have found in practice over the many years since the Poisson distribution was developed, was that it doesn't fit most data that we see in the real world. And as a result of that, another distribution was developed called the negative binomial distribution. Okay. So a lot of people are very happy just plugging along, dealing with regression or t-test or whatever, because they're very simple to explain, very simple to model, right? We can actually do it by hand if we wanted to. It's very simple to do, right? But the ordinary least squares solution assumes this linear relationship. And we also talked about the problems with using linear regression with binomial outcomes, right? One of the problems with using linear regression and binomial outcomes is that we could get predicted probabilities of less than 0 or greater than 1, right? Well, it's entirely possible with least squares regression is to get predicted counts less than 0, which is what we observed when we looked at the doctor visit. Remember when we did the doctor visit and we had that heteroscedastic error variance, right? Did anybody actually plot the number of doctor visits? No? Right, sounds like a homework assignment. Feel a homework assignment coming on. You remember when we looked at the doctor visit data, the ultimate interpretation was there's probably a better model for these data, and I said, we'll get to it. We've gotten to it. Okay. The other assumption with respect to the linear relationship is that we have this concept of equidistance, right? And yesterday in lab, we looked at confidence intervals for odds ratios. And we learned that confidence intervals for odds ratios are non-symmetrical because it's based on it's a log, it follows a log normal distribution, not a normal distribution, right? So the same thing here is that this concept of equidistance doesn't necessarily fit with these data, that the relationship is going to be nonlinear, another nonlinear relationship, right? We talked about the heteroskedasticity, right? Right, we saw that. This is actually what we saw in the number of doctor visits data set. We saw massive heteroskedasticity. So if you were to have data that had a distribution like this, or it could be the other way, right? I could have a left skewed distribution perhaps. But this is what we normally see with count data. If we use least squares, you get biased results. Inconsistent has to do with our the accuracy, and be biased and inefficient. Our standard errors would be too big. So you could do it, because we did it. We modeled count data in the doctor visit data, and we got answers. But we started to question the validity of the inferences that we would make from that model. Okay. So let's talk about the Poisson regression, fish. Right? Fish regression. So we're going to talk about these things. So the Poisson regression is going to be appropriate if we see data that we think looks like this, and we have no evidence of over-dispersion. So what's over-dispersion? Over-dispersion, the over-dispersion, or Poisson makes an additional assumption about the distribution of the data. So the Poisson distribution makes the assumption that the mean and the variance of the data are the same. All right, so it makes the assumption that the mean and the variance of the data are equal. The data are said to be over-dispersed if the variance is larger than the mean. In many data sets that we encounter, we often observe this over-dispersion. You can also have under-dispersion. A lot of times in hospital, when you deal with healthcare especially, you'll see a gigantic spike at 0. Right? How many people go to the doctor every year? There's going to be a large number of people who never see a physician, don't go for treatment, right? So what happens in that case is all of those zeros are going to shrink the variance, and you'll have an under-dispersed model. So Poisson may not fit those data either. All right, so the Poisson distribution assumes that the mean and the variance are equal. Poisson regression is also reasonable or most appropriate when the mean is small, less than 10, preferably 5. Because what happens is as the mean of count data begin to increase, what happens is that the data, oh, that's bad, you can't see that. What happens is that the data begin to look more and more normalish. And in which case, regression in that case would be quite appropriate. Okay. Okay, so a little bit of history on Poisson. So he was interested. He noticed that there was a ton of his soldiers being killed by horse kicks. You know, trauma. He was a trauma guy. Way back when, Prussian army. So he was interested in trying to figure out, what the hell's going on here, man. Right? So for some number of people, how many deaths would I expect by a number of horse kicks? It's an interesting question. I'm sure that's all been on the top of your mind. Right? It's very appropriate now, right? So he was given data for 20 years, and he was able to model the number of deaths per year by horse case. That's where this stuff came out, right? Okay. So the Poisson distribution has been used a lot, particularly in medicine, for things like measles. It's used a lot in epidemiology. How many things do you expect? How many cases do you expect, right? It's also good for doing rates. How many per 100,000? Perhaps you've seen those statistics, right? You can actually use Poisson regression for doing survival models too. How many things do you expect over some period of time?
For the rate, is it because you also expect a low rate, or is it just rates, all rates?
Rates.
Why?
Because it's some number of events over some period of time.
So, but why is Poisson appropriate for that?
It's the way that the model works out.
I just don't see how it's but it doesn't make sense in my mind why you can't just use plain logistic regression.
So that's death, yes, no. Doesn't tell you the number of deaths.
But you get a frequency, right?
No, you get a probability. It's a different question.
But doesn't it no longer become discrete if you're doing rates? Because then you're going to...
Yeah, but it's number. It's going to be an actual and expected number per some rate, per over some denominator. Okay.
So the rate is just the same thing, like what if it's 100 per year? Does that violate what you were saying before about the mean being 5?
Yeah, in that case, yes.
So it has to be things that are very infrequent?
So if it's, so we might say 100 per year, so in that case it might be 1 per 10 years, or 0.1 per 100 years.
So you would redo it so that
You could, yeah, you could. You could, all right. So I'm not going to read these to you. You can clearly see it. And I'll put this out on Blackboard if it's not there, okay? So as here, so we were trying to make the connection before about the Poisson distribution and the standard normal distribution is that we know that the normal distribution is going to be governed by a mean and a variance, right? So the standard normal distribution has a mean of 0 and a standard deviation of 1. Whereas the Poisson distribution just has one parameter that we refer to as lambda. And that's where the assumption of the mean and the variance are the same. Okay, so if you know the mean, then you also know the variance of the Poisson distribution. Okay? Okay, so you can see, okay, so what happens here is, remember here, lambda is going to be the mean, which means it's also the variance, right? So if we see a very small rate, right, we see this sort of distribution here, right? And you see what's happening to the curve as the mean gets larger, right? Does everybody see this curve here, this purple curve, where the mean is 20?
Is it getting normalish?
Yeah, it's quite normal. When you see data that look like this, go ahead, go crazy. Use least squares regression. It's completely reasonable to do that. The reason it becomes, somewhat reasonable to do that is because chances are our predicted values aren't going to, go into the negative region. Confidence intervals aren't going to go into the negative region. Right? The other thing to notice is because the mean and the variance are the same, we see more and more, the distribution becomes more and more Clady-Kurtic as the average goes up, right? The data spread out more and more and more. Okay? here is the expected value of some outcome. It's going to be governed by this function here. So here we have, once again, we're dealing with log values, right? So it's the same, the reason that we're going to use log values with the Poisson or count data is the same reason we use log values in binomial, in logistic regression. Because for us to be able to do the regression, we have to be able to work across on the real number line that goes from negative infinity to positive infinity. So we can take these rates, we take logarithms of these things, then we get back into that real number line, and then we can do some modeling. Okay? Are you guys familiar with this notation here?
Oh, factorial.
Factorials, yeah. So this is what we've been talking about here, that the mean equals the variance. This is also known as equidispersion. Same assumption as we had in all of our other models is that our observations are thought to be independent. That's a very important assumption. We talked about what overdispersion was. The other thing that happens is when we have evidence of this overdispersion, greater variance than we expect, we have different models to take into account this overdispersion. We're also going to talk about what happens to the Poisson if you do Poisson, even in the face of overdispersion. That's the model we're going to look at. So if I were to cover this up, is that scary? No, it's the same thing that you've been looking at since the beginning of the semester, right? Right? The only thing that's different now is I'm taking now a log of that expected value. Right? So that's why I keep saying that regression, it's all the same stuff. It's all the same stuff, all right? So the goal is the same as in regression before. So we're interested in estimating what's the increase in the number of events, the expected number of events given a 1 unit change in some independent variable, some predictor. It's the same interpretation as a slope as we've been doing from the beginning. So again, nothing new to learn, right? All right. All right. So here are some data. This is some data from 314 high school students. We want to model the number of days they were absent in their senior year, so we might call this the senioritis data set. Okay, all right. So we have some interesting predictors in our data set. We have what kind of program are they in? Is it a general high school? Is it a college prep program? Are they learning to be plumbers and auto mechanics? The sex of the high school student and their IQ. But first of all, let's take a look at the distribution here, right? So one of the reasons we want to plot our data is that we want to say, well, what is an appropriate distribution to try and, what is the best way? What is a reasonable model to try and describe these data, right? What do we see about these data here?
Right skewed.
It's right, it's got that classic right skewed distribution, right? We also see most of the values, so you get this giant spike at 0, right?
There's no non-negative. There are no non-negative.
No non-negative values, right? Because I can't have negative days skipped, right? Regardless of how overachieving you are, right? All that extracurricular activity. So to fit a Poisson model, I'm going to start off by looking at, my descriptive statistics. Same as it ever was. Talking heads, right? So the other thing, let's talk about this again, right? Why are we interested in looking at these descriptive, these univariate statistics for these things?
You have to look at your assumptions, like the mean and the variance.
Okay, right. Right. The other thing that we're also going to be interested in looking at that, this is a subtle thing, but it's really important, right? What would happen if one of these had no variance in it? Or very restricted variance, very small variance? What do you think would happen? Right? So think of a scatter plot. Envision a scatter plot in your head. If one of the two variables in that bivariate relationship had no variance, could those two variables correlate with each other? Why not? Or you'd either see a vertical line or a horizontal line. So if it's a vertical line, that means that, well, since my x value doesn't change, there is simply no relationship with that y value. And if it's a horizontal line, I essentially have a slope of 0, which means that it doesn't matter what my x value is, my y value isn't changing systematically from it, right? So for us to be able to observe relationships between the data, there's got to be some variance, right? So sometimes when we have non-significant results for our regression coefficients, it might simply be because there's no variance in one of the predictors. There's very little variance. You need variance to make distinctions along some continuum. Right? If there's no variance, then there's no continuum. Right? So that's the other thing that we want to look at. It's a very subtle thing, but in interpreting data, if you see something as non-significant, go back and look at the univariate statistics. Is there any variability in that predictor? And that could explain why there's no relationship. Okay, the other thing I'm interested in looking at here is, what is that assumption that I had with the Poisson, that equidispersion thingy-majiggy?
The mean and the variance.
The mean and the variance are the same, right? Here's the mean, here's the variance. We've probably violated that assumption. You think that stops people? No. Let's be ignorant. Let's keep moving forward. Okay, all right.
How often do you actually end up with a data set where the mean is equal to the variance?
Actually, in 25 years of doing this, never.
How close is the thought of that kind of?
There's some leeway there, but if you have a mean of 5 and a variance of 45, they're not the same.
Wow.
They're not the same. But we're going to see what happens when we model the data as a Poisson, ignoring the over-dispersion. Right? Because like I said, and like you guys have now you guys are beginning to notice when you're reading the articles, hey, they never talked about any of the assumptions. They just went forward with things, okay? Okay, all right, so is anything new on this screen that you've not seen before? This is all, seen all this, right? It's a likelihood ratio, right? We're dealing with the same things we did with logistic regression. Why do we have 4 degrees of freedom for this chi-squared? 1, 2, 3, 4 parameters, right? Number of observations. What is this chi-square testing? What is this p-value? What is all that? It's testing against what?
The intercept.
The intercept-only model. Is the model better than nothing? Right? Is the model better than nothing? So we can say, oh, this model is better than nothing. We have some evidence to suggest that the model is better than nothing. This is our pseudo R-squared, McFadden's again. Okay. Okay. And remember, these are log values, right? Just like we saw in the logistic regression. So, what can we say, right? So, females are more or less, being female is associated with having more or less days skipped or days missed. Females positive. Females
More.
tend to have more, right? How about your IQ? Did any of you guys skip class your senior year?
Yeah.
Yeah. A lot.
Not a lot.
Not a lot.
I didn't believe it.
You overachievers, you. Right, so bright people tend not to miss school. We had a policy in my school district when I was going to school where if you skipped class, you had 2 points taken off your final grade. I graduated high school with a D- average, a 1,500 on my SATs, and 6 AP course credits. I never went to class. All right, so it's true.
I
But
love
how
it.
did you go to college if you had a D- average?
I was an all-American wrestler.
Oh, wow.
Plus, I had awesome grades. I mean, except for the grades.
Where'd you wrestle?
In Pennsylvania.
Oh, I'm curious.
All right, so here we have general and vocational. What's missing? Which group, which category is missing? College prep, right? So now we know how to interpret the intercept, right? So the intercept is going to be what? How do we interpret that value of the intercept? So it's going to be a male with no brain, no IQ points, who's in the college prep program. Make sense? That's how we interpret those things.
It's not like average IQ, what is that?
For every 1 unit increase in IQ, we expect the number of days missed to change by this log amount, by this, if I were to exponentiate this.
So we actually, you're like, with lowest IQ is 0 IQ?
No, this is now a model, right? We can write this down as a model. So we would write down,
It's an intercept that was male with no brain.
yeah, with no brain, no IQ.
Literally no IQ.
No IQ, because the intercept is what is the expected value of y when all of the x's are 0. So if female is 0, we're dealing with a male. If IQ is 0, then that's IQ is 0. If general and vocational are 0, then that means college prep. It's the same interpretation as every other regression that we did. Okay. Okay, so the others say there is something new here, right? So yesterday we did the ESTAT GOF, which GOF is not GOF, it's goodness of fit, right? It's goodness of fit. The assumption here, the hypothesis that we're testing here is there is no deviance. There's no over-dispersion. The model be fitting the good, fitting the data good. We suddenly become Jamaican. I and I are already. No? Okay, all right. So here, what's this, you know? How good is the fit? The technical term is, oh crap, oh, it sucks. It doesn't fit the data. The data don't fit the model at all. When we look at our goodness of fit statistics, just like yesterday, and with the logistic regression models, we want to fail to reject the goodness of fit test. Because the hypothesis, the null hypothesis for the goodness of fit is the data fit the model. We reject it here. These data do not fit the model well at all. As Lucy would say, or Desi would say, Lucy, you got some splaining to do. No? I love Lucy.
Oh, okay.
I love that.
I'm not familiar, but I will.
Okay, all right. So this actually, I mean, does this surprise anybody, right? These enormous statistics here, these chi-square statistics, they're enormous, right? Given that you guys are so smart, I know you have in your head that the mean was 6 and the variance was 49.5. right? So it shouldn't come to anybody's surprise that the data don't fit the model at all. Right? So we have to ask the question, is the model wrong or are the data wrong?
Model.
Most likely the model. Okay. All right. So let's move ahead. All right. Anyway, and let's see what happens when we do this we fit these models in the presence of over dispersion. All right. So, what do we see here? Okay. So remember that these are going to be log number of events, right? That's what the coefficients from the model come to. They're log number of events. So, right. So since we're dealing with a binary variable here, what we can do is if I were to exponentiate 0.24. Does anybody have a calculator? Exponentiate 0.24. 1.27. I'm just going to throw this away. So if I exponentiate 0.24, I get 1.27. How do I interpret that? Well, females, on average, their rate of skippage, their rate of days missed is about 1.27 times higher than males, right? Or what we can do is just subtract 1 to give us that 0.27 multiplied by 100 to say that females miss on average about 27% more days as compared to females can miss about 27% more days on average as compared to males. Right? It's the same exact thing that we did for our odds ratios. Right? Except these aren't odds ratios now, these are rates, right? The number of days missed here. You guys, you believe me? You believe me now that all of this stuff is the same? It's all the same. Getting there, good.
So when you report these, like in a table or something, appropriate name for that 1.27 is a relative rate, or what do you
It's the expected effect on number of days missed for a female as compared to a male.
There's no short, it's like that column would be the odds ratio.
Oh, no, it's a beta coefficient.
The one with the exponentiated
Yeah.
coefficient beta.
No, this is the beta coefficient here.
Right here.
Oh, so it doesn't have a special name like a logit, because it's not a log odds. It's a log count. That's what it is. It's a log count.
Okay, so like in the table of like a Poisson regression, you would label that column
Coefficient or beta.
But I mean the exponentiated.
Oh, effect.
Okay.
Okay. Alrighty. Okay, so we do the same thing for IQ, and if we exponentiate IQ, what's the exponent of, if I were to take e to the negative 0.007, what do I get? Minus 1. Right, so you said it was point what?
993.
Okay. Okay. So, since this is lower than 1, the rate is. Are you sure it's not improved?
Yeah.
Maybe not.
And then minus 1, it's negative 0.0069.
The inverse of this.
Yeah. Minus 1.
If 0.993 minus 1.
Yeah.
She's saying.
Yeah. Okay.
0.005.
Okay. All right. Okay, so we get this, right? All right, so, okay. So if we do this math here, right, we're going to say that having an IQ, the higher your IQ, the lower the expected number of days you missed, right? So if we put it all together just like we did with every other regression, right? So here we have our intercept, right? Here we have our intercept. We have the effect for being female, the 0.24. The effect of being in a vocational group, and the effect of somebody having an IQ of 50. Their expected number of days missed is 3.12. Does that make sense? So again, this is why we report the betas. Because I can't take these values here that we've come up here and add them together to come up with the expected days. I have to put the whole thing in the equation. Exponentiate that. Make sense? Right, so it's nothing new. It's what you've been doing forever and ever. Okay, so we know that there was a problem with the data, that the deviance test to see if there was over-dispersion was just like red flag, red flag, red flag, problem, problem, problem. The mean of 5 and a variance of 49.5, not the same. All right, so let's look at alternatives to this, okay? So the problems with doing Poisson with this is that Poisson is consistent. A consistent statistic means that as the sample size gets larger, the values converge to the true value, right? But as the sample size gets larger, you still have what we refer to as an inefficient statistic. So that means that the standard errors are too large. So what would happen if our standard errors were too large? What are the inferential problems of having a standard error that's too large? Remember how we get the test statistic? We divide the standard error into the coefficient to get the test statistic. So if this value is big and this stays the same, what's going to happen to the test statistic? It's going to be small. As the test statistic approaches 0, what happens to the p-value? It gets big. So if we connect all those dots, what are the potential inferential implications for fitting data to a model for which the data don't fit? You lose power. Right? And what are the consequences of that?
You need to enroll more people.
You can't make as many inferences. You can't make as many conclusions.
Well, you made a conclusion, but what's the likelihood of the conclusion now? Is the conclusion correct or incorrect?
It's more likely to be incorrect.
In this case, you run a higher rate of making a type 2 error. Right? So it's another case of, well, this thing doesn't work. When in fact, the thing that you're studying may work. You just didn't fit a model that fit the data very well. So you may have erroneously thrown out an intervention that in fact works based on faulty inferences, faulty assumptions about the data, which has consequences far beyond the statistics. Right? Make sense?
This is probably a really stupid question, but obviously when we read journal articles, we only see the model that they used. We don't see all the others that they tried to use and potentially rejected, right? I mean, we don't, yeah.
I would encourage you, if you're going to try different models, is to write about them and choose and explain why you settled on this model versus the other models.
But, so would you do you think that that's more standard, is that people try?
I bet most people don't even look.
Oh, okay.
I refer to your colleague who shall remain nameless, who said, I just thought statistics was you take a bunch of number, throw it to the computer, and you're done.
Who said that? One of the cardiologists?
No. I told you I'm not going to throw anybody under the bus, but it's not uncommon for students in this class who have taken this class and probably will take this class to make the same assumption. Oh, I'm just going to throw data in the software, and the software is going to give me a number. Uh-huh. Sure it is, yeah. In most cases, it's going to give you a number. Right? It's a computer. It's stupid. It's going to do what you tell it to do. It's up to you, the human being, the subject matter expert, to make proper inferences based on what you observe. Computers are stupid.
So, like, let's say that I was studying rates of something, right? So I said I want to use a Poisson regression.
Mm-hmm.
And then I look at all my data and the variance and the mean are not equal.
Mm-hmm.
At that stage, then, should I use it, like...
A different model?
Yeah.
Yeah, probably.
Okay.
Yes.
Okay.
What you would do in the write-up is you would say you initially thought of this as a Poisson. You were initially going to do it as a Poisson regression. However, you observed great, this over dispersion. So then you went to fit a second model.
Got it. Okay.
Which is, I would much rather, as a consumer of the research, because now you've actually told the reader two things. One, you got the final model, but you've also told them what you learned about fitting the first model, is that we have this over dispersion problem, which by definition means that there's more variance than the expected value. Right? Okay. All right. All right. So, what do we do in this case of over dispersion? Right. All right. Okay. Okay. So what we can do is we can fit an over dispersed Poisson model, so we can actually acknowledge the over dispersion, or we can fit a negative binomial regression model. So there are options out there. So that's okay. Okay. So, to fit an over-dispersed model, what we're going to do is, can you see this? This says GLM. It's just regression, baby. That's all it is. It's just regression. Essentially, what we're going to do is we're going to rescale the data. So that's what an over-dispersed Poisson model is. It rescales the data. So all of this stuff is the same here. Right? These are AIC and BIC that we saw yesterday. Right? Okay. Now what happens here is when you fit the model this way, it tells you that the standard errors are scaled. The coefficients aren't going to change, right? Because that we said that it's consistent but inefficient. Right? So consistent means that we get these unbiased point estimates. It's the standard errors that are going to be wrong. So what's going to happen is that the standard errors that we saw before are going to be scaled by some normalizing factor. Okay, so it's going to shrink the standard errors. So let's write this down for a second. So for female, we had 0.242 as our beta, and the standard error is going to be 0.119. Okay? Bada bing. Okay. All right. Okay. 652. This is 0.5, so this is the square root of 0.625.
I had to think about what's next to the x.5 meant.
It's a square root.
Yeah.
This.
It took a second.
It's this. It tells you that. Okay. All right.
Is that how they're always scaled? Or they get scaled down?
They're going to be scaled to the square root of the chi-square.
Oh, it's with
Over dispersed model.
So it's just, it makes it like a more conservative sort of estimate, right?
Okay. get it? Okay, so the negative binomial model. Oh, the other thing to notice here, crap, is the other thing that's missing in the Poisson model. Do I have it? No, I don't. Yeah, I did somewhere. Did anybody notice that our friendly error term was missing? That's because we assume the mean and the variance are the same. Well, no, we assume that the mean and the error are the same. The variance are the same. Keep that in your head. Now let's go to the negative binomial model. Now we reintroduce the error term, right? Because we're assuming that the outcome is equal. But aside from this, it looks exactly the same now, doesn't it? Right? So let's say, what would happen? What do you think would happen to the negative binomial model if we fit a negative binomial model to data that actually fit the Poisson distribution? Say again? It would be the same, right? This would be 0 and would go back to a Poisson model. So why anybody would do a Poisson model is, I don't know. Okay, all right. Okay, all right. So how do I do a negative binomial regression? It's really hard. I use an NBReg command, same format, same syntax, right? Okay. Okay, now, this alpha down here is that estimate of that error term. Is there over dispersion? Notice what happens to the coefficients for female there. Pardon?
It went down.
A little bit smaller. A little bit smaller. What about the standard errors?
A little bit bigger. Bigger.
A little bigger. So this model probably fits the data a little bit better, because now we're taking into account that over dispersion. We're allowing that extra variance in the model. So here are the two model estimates. Here are the two models side by side. Do you see any substantive differences between these two models?
We no longer add statistical significance at the 0.25 level for female.
For female, right? Okay. Right. But what about the coefficients? Essentially the same. Essentially no difference with respect to the point estimates. The reason I show this is to sort of drive home the idea that in the face of over dispersion, the Poisson model is consistent. I'm sorry, it's consistent in that the point estimates are on average about correct. Right? What happens here is that here we are not acknowledging the variance. We are not acknowledging that over dispersion. Bad. 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 All right? So here we're allowing for that extra variance. And in general, the inferences don't change except for female here. Right? Okay? Make sense? Okay, so putting it all together, here's what we have. Right, so this is how I would do this over-dispersed Poisson model. Stay using the GLM. The reason I'm showing you this is if you're going to learn one command in Stata, one modeling command in Stata, learn GLM. Because if you learn the GLM command, then you can do least squares regression, you can do logistic regression, multinomial, Poisson, negative binomial over dispersed, because they're all the same thing.
Just in terms of the code, like where you have, I understand, so can you go through it? So
Yep,
really-
okay, so here's the model, right? GLM, generalized linear model, here's my outcome, I dot female is the code that retells, the I dot tells Stata that this is a factor. This is a factor. What is the probability distribution that I'm assuming the data to follow?
What would be the other option? So you put like family, and you put
Family could be
NB-reg.
logit, NB-reg, could be a whole bunch of other things, all
Okay.
these models that we've been talking
Sure.
about. The link is how we believe this is going to be modeled. So we're going to take the log of this outcome, okay? And this tells me to scale my standard errors by that x2 is really chi-squared.
Oh.
The reason that we can, if I were to give you one piece of advice, you're going to learn one Stata command and learn GLM, is because it's all the same. The only thing that would change from one different model to another would be these two things. It's all the same.
Can you do that though instead of doing, can you put Poisson in the front and leave out the GLM and leave the other stuff? You have to do it that way.
Oh no, the Poisson command is a wrapper for this. Meaning, underneath it all, it's essentially going to do that for you.
So what was the link command again?
The link is going to be how the outcome is going to be modeled. So it's not number of days that this is going to model. It's going to actually model the log number of days.
What if you wanted to do the number of days, like if you wanted to do something else, what are the other things that you might type in there?
With respect to the link function,
Yeah.
you could actually take out the link function, and then it would be just left alone. But it kind of wouldn't make sense.
So the link would be log for like logistic regression,
Yeah.
Poisson.
You can put it on your link.
So you're just doing a linear regression, what would link?
There would be no link. You would have an identity family.
So family would be.
Family would be identity, the word identity, which tells Stata that you're assuming a normal distribution. And there'd be no link function because you're not doing anything to the outcome.
And you always use chi-square.
Well, you wouldn't need to do a scale if you were to do a least squares regression. Right? Just take a look at the documentation for the GLM function. All right, so we've used the margins command before. All right. So what I'm going to try and do here is I fit my over-dispersed Poisson model. Then the next command I could execute is the margins command. So here would be what is the expected number of days missed for combinations of program and sex for a person with an IQ of 50. So we were asking questions before is how do I set those values to be a specific value? All right, so here's what we have here. So program 1, I think was the general, right? So the expected number of days missed for someone in the general program who is a male is 8.7 days. Right? The expected number of days missed for a female who is in the general program is 11 days. Right? Make sense? That's how we do this. Okay, there are extensions to these models. So what I want to talk about here quickly, because we're out of time again, is that if we see this case here where there's a ton of zeros, we have the concept of under-dispersion, we can have what are called zero-inflated models. So there are things called zero-inflated Poisson or ZIP models, or zero-inflated negative binomial models, right? Okay. We can have what are called hurdle models. So do you remember when we fit the continuation ratios in logistic regression, right? You can have the same concept in a hurdle model, right? If you were to play the 99 bottles of beer on the wall game, to get to the 90th bottles of beer on the wall, first you have to drink the first 10 bottles, right? So you can't go from 90 bottles of beer or 100 bottles of beer on the wall right to 90, right? Unless you're power checking, but that's not how you play that game. Right? So you can fit this hurdle model, which is sort of the analog to that continuation ratio model that we fit in logistic regression, right? Okay. So what we'll do Tuesday is we'll do an example of this in class, okay? So if you could look in the literature and see if you can find an example of count data being modeled. I'd be interested to see how people are doing this in your fields, in your respective fields. Okay, fair enough? Okay, I'll go and put this presentation out on Blackboard right now, so I don't forget. Okay? All right, that's it.